Welcome! In this session, we'll explore an interesting computational geometry problem from LeetCode, problem number 939, minimum area rectangle. Together, we'll break down the problem, analyze different approaches, and develop an efficient solution. Let's dive in. In this problem, you are given an array of points, where each point is represented as x, y, indicating its position on a 2D plane. The goal is to find the smallest possible area of a rectangle that can be formed using any four of these points, with the condition that the sides of the rectangle must be parallel to the x-axis and y-axis. If it's not possible to form such a rectangle, you should return 0. For the input, the array points can have between 1 and 500 elements, and for each point, both the x and y coordinates are integers ranging from 0 to 10,000. The output will be a single integer, representing either the minimum area of the rectangle or 0 if no rectangle can be formed. Here's an example to understand the problem better. For the input points equals 1, 1, 1, 3, 3, 1, 3, 3, 2, 2, the output is 4. The points 1, 1, 1, 3, 3, 1, and 3, 3 form a rectangle. The area of this rectangle is 4, calculated as the difference between the x-coordinates, which is 3, 1 equals 2, multiplied by the difference between the y-coordinates, which is also 3, 1 equals 2. The point 2, 2 does not contribute to forming any valid rectangle. In another example, if the input is points equals 1, 1, 1, 2, 2, 1, 2, 2, the output is 1 because the points 1, 1, 1, 2, 2, 1, and 2, 2 form a rectangle with an area of 1. Now consider a case where no rectangle can be formed. For the input points equals 1, 1, 1, 3, 3, 1, the output is 0 because there are only 3 points, and a rectangle requires at least 4 points. Since no 4 points satisfy the rectangle condition, the result is 0. The constraints of the problem specify that the input array will have between 1 and 500 points, all of which are unique, and the x and y coordinates will always fall within the range of 0 to 10,000. Finally, let's discuss some edge cases. If the input contains fewer than 4 points, such as 1, 1, 2, 2, no rectangle can be formed, so the output is 0. Similarly, if all the points lie on a single line parallel to either the x-axis or y-axis, no rectangle is possible, and the output is again 0. If multiple rectangles can be formed, the task is to return the area of the smallest rectangle. On the other hand, if the points are scattered in such a way that no valid rectangles can be formed, the output should also be 0. These considerations ensure your solution is robust and handles all possible scenarios. To start, we can consider the brute force approach, which is the most straightforward way to solve the problem. The idea here is to iterate through all possible combinations of 4 points in the input and check if they form a rectangle. For a valid rectangle, we need the sides to be aligned parallel to the x-axis and y-axis, which means opposite sides must have the same x or y coordinates. Once we identify a valid rectangle, we calculate its area and keep track of the minimum area found. However, this approach has a significant drawback in terms of complexity. Since we need to evaluate all combinations of 4 points, the time complexity is n to the power of 4, where n is the number of points. For larger inputs, such as n equals 500, this becomes computationally prohibitive. Additionally, the space complexity is 1, but the excessive runtime makes this approach impractical for solving the problem efficiently. To address the inefficiency of the brute force method, an optimized approach leverages a hash-based strategy. This method is built on the observation that a rectangle is uniquely defined by 2 pairs of points that share the same x or y coordinates. For example, if we have 2 points, x1, y1, and x2, y2, they can form the diagonal of a rectangle if the other 2 corners, x1, y2, and x2, y1, also exist in the input. Using this insight, we can optimize the solution with the following steps. First, we use a hash set to store all input points, enabling O1 existence checks. Next, we iterate over all pairs of points in the input. For each pair, we check if their diagonally opposite corners exist in the hash set. If they do, we calculate the area using the formula abs, x2, x1, asterisk abs, y2, y1, and track the minimum area found. This method significantly reduces the computational overhead, bringing the time complexity down to O(n squared), as we only need to consider pairs of points, and the space complexity is O(n) to store the hash set. The hash-based approach is particularly advantageous because it drastically reduces the computational effort compared to the brute force method. With O(n squared) complexity, it is much more efficient for larger inputs. An alternative way to optimize the solution is through column-based iteration. This approach involves grouping points by their x-coordinates. Specifically, we create a dictionary where each key represents an x-coordinate, and its value is a list of associated y-coordinates. Then, by iterating over pairs of y-coordinates within each column, we track the last x-coordinate where this pair occurred. If the same pair is encountered again, we calculate the area using the difference in x-coordinates. While this method is also efficient with a worst-case time complexity of O(n squared), it can be harder to implement and debug due to the added complexity in iterating and managing column-based data. For these reasons, the hash-based diagonal checking method is generally preferred for its simplicity and clarity. The optimized approach using hash-based diagonal checks stands out as the best strategy for solving this problem effectively. By focusing on the key observation that rectangles are defined by diagonally opposite corners, we can use hash sets to perform quick existence checks and eliminate unnecessary computations. This insight, combined with the simplicity of iterating over pairs of points, reduces the problem to O(n squared) time complexity, making it efficient for large inputs. While the column-based iteration method also achieves similar efficiency, it is less straightforward to implement, which can introduce additional challenges during debugging. The hash-based approach strikes an excellent balance between efficiency and clarity. Although it uses slightly more memory, this trade-off is well worth it for the ease of implementation and the reduction in runtime complexity. Overall, this strategy provides a clean, fast, and reliable solution to the problem. In this problem, we are tasked with determining whether any 4 points from a given set can form the vertices of a rectangle on a 2D plane. A rectangle must have 2 pairs of opposite sides that are parallel to the x-axis and y-axis and must include 4 right angles at its vertices. The input is a list of points, where each point is represented as a pair of integers, and the output is a Boolean value indicating whether a rectangle can be formed. For example, if the input contains points like 1, 1, 1, 3, 3, 1, and 3, 3, these form a rectangle, so we return true. But if the points are 0, 0, 1, 1, and 2, 2, we cannot form a rectangle due to insufficient alignment, so we return false. A brute force approach would involve generating all possible combinations of 4 points from the input list and checking whether they satisfy the rectangle conditions. This step involves computing combinations, where the total number of subsets of 4 points is determined by the formula CN4. Next, for each combination of 4 points, we need to validate whether they can form a rectangle. To do this, we check the coordinates of the points. Specifically, a rectangle must have 2 unique x-coordinates and 2 unique y-coordinates among its vertices. For example, given points x1, y1 x2, y2, x3, y3, and x4, y4, we verify whether the x-coordinates form 2 distinct pairs and the y-coordinates form 2 distinct pairs. If this condition is satisfied, then the 4 points form a valid rectangle. If any combination of points meets these criteria, we can immediately return true. Otherwise, if no such combination exists, we return false. Additionally, there are some edge cases to consider. For instance, if the input list has fewer than 4 points, we can directly return false since it's impossible to form a rectangle. Similarly, we need to handle duplicate points in the input and ensure that our algorithm correctly identifies cases where points lie on the same line, as these cannot form a rectangle. To deepen our understanding, let's highlight some key insights about the problem. A rectangle is defined by 2 pairs of parallel sides, meaning that the x-coordinates and y-coordinates of its vertices must align appropriately. This alignment can be efficiently verified by checking the uniqueness of the x and y values. However, the brute force approach of generating all combinations of 4 points has significant computational overhead. Generating combinations takes CN4, which is O(n to the power of 4, in the worst case. Since checking whether a combination forms a rectangle takes constant time, the overall complexity becomes O(n to the power of 4. To improve efficiency, we can introduce optimizations. For instance, we can store all points in a hash set, which allows for faster lookups. Additionally, instead of evaluating all combinations, we can pre-compute pairs of points that share the same x or y coordinate, which helps reduce redundant checks. To implement the optimizations, we can use data structures like hash sets and dictionaries. A hash set is ideal for storing all the points because it provides O(1) lookup time, which is critical when verifying whether the diagonal points of a potential rectangle exist. Alongside the hash set, we can use a dictionary to group points based on their coordinates. For example, we can create a dictionary where the keys are x coordinates, and the values are lists of y coordinates that share the same x coordinate. Similarly, we can group by y coordinates. These groupings allow us to efficiently identify potential pairs of points that could form the sides of a rectangle, significantly reducing the need to explicitly check all combinations of 4 points. Building on these optimizations, the steps of the optimized algorithm begin with pre-processing the points. First, we store all points in a hash set to enable constant time lookups. Then, we iterate through all pairs of points. For each pair, we check if they share the same x or y coordinate. If they don't, we calculate the potential diagonal points that would complete the rectangle. Using the hash set, we verify whether these diagonal points exist. If they do, we know a rectangle can be formed, and we return true immediately. If no such rectangle is found after examining all point pairs, we return false. This approach avoids the inefficiency of checking all combinations explicitly by leveraging the structure of the input and the hash set for quick lookups. Finally, let's analyze the complexity of the optimized approach. First, pre-processing the points into a hash set takes (n) time, where n is the number of points in the input. Next, iterating through all pairs of points involves (n squared) operations since there are n choose 2 pairs. For each pair, checking whether the diagonal points exist in the hash set takes (1). Therefore, the total time complexity of the optimized algorithm is (n squared), which is a significant improvement over the brute force approach. This reduced complexity makes the algorithm feasible for larger inputs, making it both efficient and practical for real-world applications. This solution begins by creating a set of the input points for efficient lookup operations. The algorithm then iterates over all possible pairs of points, x1, y1, and x2, y2. If the 2 points are neither on the same x-axis nor the same y-axis, they could potentially form the diagonal of a rectangle. To confirm this, we check if the other 2 corners of the rectangle, x1, y2, and x2, y1, are also present in the set. If all 4 points exist, the area of the rectangle is calculated as the product of the absolute differences in their x and y coordinates. The minimum area is updated if the calculated area is smaller. After iterating through all pairs, if no rectangle was found, the function returns 0, otherwise, it returns the smallest area found. This approach ensures that all possible rectangles are considered while maintaining efficiency through the use of a set for constant time point lookup. Here, we start implementing the solution in Java. First, we import the necessary utilities and define the solution class. The main method, minAreaRect, accepts a 2D array of points as input. To optimize our lookup operations, we use a hash set to store all the points in a format that combines their x and y coordinates as a string. This allows us to quickly check for the existence of specific points later in the process. Next, we initialize a variable minArea to integer.max_value to keep track of the smallest rectangle area found so far. We then use a nested loop to iterate over all pairs of points in the input. For each pair, we extract their x and y coordinates. The goal is to determine if these 2 points can form the diagonal of a rectangle. For that to happen, their x and y coordinates must differ, ensuring they are not aligned vertically or horizontally. If this condition is met, we proceed to check if the other 2 corners of the potential rectangle exist in our hash set. This ensures we have all 4 points necessary to form the rectangle. If the other 2 corners are found, we proceed to calculate the area of the rectangle. The area is determined by the absolute difference in x coordinates multiplied by the absolute difference in y coordinates. We then compare this calculated area with the current minimum area and update the minArea variable if the new area is smaller. This ensures that by the end of the loops, minArea will hold the smallest rectangle area found among all valid rectangles. Finally, we handle the case where no rectangle could be formed. If min area remains unchanged at integer.max_value, it means no valid rectangles were found, and we return 0. Otherwise, we return the value of min area as the result. This concludes the implementation, ensuring an efficient solution to the problem using hashing and nested iteration. To solve the problem, we start with example 1. The input consists of points located on a 2D plane, and our goal is to find the minimum area of a rectangle that can be formed using these points as corners. First, we convert the list of points into a set for efficient lookup. This allows us to quickly verify the existence of specific points without repeatedly searching through the list. Here, the point_set is initialized, and we also initialize min_area to infinity as we are searching for the smallest possible rectangle. Next, we iterate through all pairs of points. For the pair 1, 1, and 1, 3, they cannot form a diagonal because they share the same x-coordinate. Similarly, 1, 1, and 3, 1, cannot form a diagonal because they share the same y-coordinate. However, for the pair 1, 1, and 3, 3, the x and y coordinates differ, so they form a potential diagonal. Now, we check if the other two corners of the rectangle 1, 3, and 3, 1 exist in the point_set. Since both points are present, we calculate the area of the rectangle as abs, 3:1, abs, 3:1, which equals 4. This becomes our current min_area. We continue checking other pairs of points, but no smaller rectangle is found. Therefore, the minimum area for this example is 4. Now, let's consider example 2, where the input points are 1, 1, 2, 2, 3, 3. Once again, we begin by converting the list of points into a set, so point_set is initialized, and we set min_area to infinity. We then iterate through all pairs of points to check if they can form the diagonal of a rectangle. For the pair 1, 1, and 2, 2, the x and y coordinates differ, making them a potential diagonal. To confirm this, we check if the other two corners 1, 2, and 2, 1 exist in the point_set. However, these points are not present, so no rectangle is formed. We proceed to check other pairs of points, but none of them satisfy the conditions for forming a rectangle. As a result, no rectangles can be constructed from this set of points, and the output is 0. In example 3, the input consists of points 1, 1, 1, 4, 2, 1, 2, 4, 3, 1, 3, 4. After converting the points into a set, point_set is initialized, and we set min_area to infinity. We now iterate through all pairs of points to identify potential diagonals. For the pair 1, 1, and 2, 4, the x and y coordinates differ, so we check if the remaining corners 1, 4, and 2, 1 exist in the point_set. Both points are present, so we calculate the area of the rectangle as abs, 2:1, abs, 4:1 equals 3. This becomes the current min_area. Next, we consider the pair 1, 1, and 3, 4. Again, the x and y coordinates differ, and the other corners 1, 4, and 3, 1 are found in the point_set. The area of this rectangle is abs, 3:1, abs, 4:1 equals 6, but since min_area is already 3, it remains unchanged. We continue examining other pairs of points, but no rectangle with a smaller area is found. Therefore, the minimum area for this example is 3. Here, we start analyzing the time complexity of the solution. The first step involves iterating over all pairs of points. For each point, we loop through all subsequent points, resulting in a total of n*(n1/2 unique pairs. This simplifies to O(n²), which is the cost of this step. Next, for each valid pair of points that can form the diagonal of a rectangle, we perform two constant time lookups in the set to check if the other two corners exist. Since each lookup in a set takes O(1) on average, this step adds an O(1) cost per pair. Finally, calculating the area of the rectangle and updating the minimum area is also an O(1) operation. These constant time operations per pair do not change the dominant O(n² complexity from the first step. When we consider the total time complexity, the O(n² cost of iterating over all pairs of points dominates the overall computation. While the set lookups and area calculations are constant time operations, they do not scale with the number of points and therefore do not impact the asymptotic complexity. As a result, the total time complexity is O(n squared). Moving on to space complexity, the algorithm uses a set to store all the points for efficient O(1) lookups. The space required for this is proportional to the number of points, which is O(n). Additionally, a few auxiliary variables are used, such as for tracking the minimum area or the coordinates of points, but these require constant space, O(1). Therefore, the dominant factor in space complexity is the set of points, leading to an overall space complexity of O(n). Now let's break down the best, average, and worst-case scenarios for the algorithm. In the best case, if there are fewer than 4 points or no rectangle can be formed, the algorithm can terminate early without iterating over all pairs of points. This results in a time complexity of O(1). In the average or worst case, the algorithm needs to evaluate all possible pairs of points to find the minimum area rectangle. This involves the O(n squared) iterations we discussed earlier, making the average and worst case time complexity O(n squared). Finally, let's compare this approach to a brute force method. A naive approach would involve considering all combinations of 4 points and checking if they form a rectangle. This requires evaluating (n) for combinations, which results in a time complexity of O(n to the power of 4). In contrast, the current solution improves significantly by focusing only on pairs of points as potential diagonals. This reduces the problem to O(n squared), with constant time set operations for corner validation. This improvement is particularly impactful for larger datasets. The mathematical proof also supports this, since the pairwise iteration dominates at O(n squared), and set operations and area calculations do not scale with n, the total time complexity remains O(n squared). Space complexity, driven by the set of points, stays at O(n), making the solution both efficient and scalable. When tackling this problem, there are several common mistakes to watch out for. First, a frequent error is not properly validating rectangle conditions. It's easy to assume that any 4 points will form a rectangle, but that's not the case unless you verify that opposite sides are both parallel and equal in length, and that all angles are right angles. Without these checks, you might end up with incorrect results, as not all 4-sided figures are rectangles. Another issue is ignoring edge cases. For instance, if some points overlap or if there are fewer than 4 points, your program might crash or produce invalid outputs. You also want to avoid inefficient brute force implementations. Checking all combinations of 4 points without using optimizations, like sorting or hashing, can lead to an O(n to the power of 4) complexity, which is impractical for larger datasets. Lastly, floating point precision issues can arise if you use floating point arithmetic to calculate distances or angles. Due to imprecision in floating point comparisons, you could get incorrect results. These are critical pitfalls to avoid for a robust solution. Now, another challenge is the incorrect use of data structures. For example, using lists instead of sets to store in checkpoints is inefficient because lists have an O(n) lookup time, whereas sets provide O(1) lookups, which can significantly speed up your operations. Shifting gears to interview strategies, it's essential to understand the scope of the problem. Determine whether rectangles must be axis-aligned, which simplifies the calculations, or if any orientation is allowed. Hashing also plays a key role in efficiency. By storing points in a set, you can achieve constant time lookups, making your algorithm much faster. Additionally, geometry problems like this often require verifying specific properties, such as distances or slopes, so be prepared to derive these mathematically. Finally, when discussing solutions, always acknowledge trade-offs. If you start with a brute force approach, explain its inefficiencies and suggest optimizations, like reducing combinations or leveraging a hash set for better performance. This problem also relates to other common geometry problems you might encounter, such as LeetCode 149, which involves finding the maximum number of points on a line, or LeetCode 356, which deals with line reflection. Of course, we're currently focused on LeetCode 939, but another interesting problem is LeetCode 587, which involves constructing the convex hull for a set of points. Considering alternative approaches, the brute force method involves checking all combinations of 4 points to determine if they form a rectangle. While this approach is straightforward and easy to implement, it's computationally expensive with an n to the power of 4 time complexity, making it unsuitable for large datasets. A more efficient alternative is using hash set optimization. By iterating through pairs of points, you can compute their diagonals and check if the other 2 points exist in a hash set. This brings the complexity down to n squared, though it does require additional memory for the hash set. This trade-off between time and space is a key consideration when choosing your approach. Another advanced method to consider is the sweep line algorithm. This approach involves sorting the points and then using a sweep line technique to find rectangles. It's particularly useful for certain variations of the problem, especially when the input is structured in a way that benefits from spatial ordering. However, while this method can be highly efficient, it's also more complex to implement and may require additional effort to fully understand and debug. This makes it a good option for edge cases where other methods might fall short, but it's important to assess whether the added complexity is worth the potential efficiency gains in your specific scenario. Great work! To recap, we tackled the minimum area rectangle problem, discussed key strategies, and highlighted the importance of hash maps in optimizing solutions. Remember, computational geometry problems often test both algorithmic thinking and practical implementation skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!